Welcome to lecture series on advanced linear algebra. We have seen over a finite dimensional inner product space, if we consider any linear functionals, then there exists a unique vector over the space, so that linear functionals is basically inner product of that fixed vector. And we have also seen if a linear operator defined over a finite dimensional inner product space, it has adjoint operator on it. Today we will see how to find that unique vectors when a linear functional defined over a inner product space. So, let me consider this problem where V be the vector space of polynomial functions over the real line of degree less than or equal to 2, and the inner product defined in this space is defined by inner product of f g equal to integral 0 to 1 f t g t dt. For a fixed real number set T naught belongs to R, which is constant if I consider, let me define a linear functionals phi from V to R as phi of f equal to function value at T naught. So, since we already know this function phi from V to R is a linear functional, so now we are interested to find a function or an element in V say G such that the phi of f equal to inner product of f and G for all f belongs to V. So, now if you recall the theorems, we need basically an orthonormal basis for the space V, and then the unique element, if we recall that beta, here it will be something G, is will be basically equal to sigma phi of that orthogonal basis element, suppose alpha 1 to alpha n, phi of alpha I, sigma f of alpha I bar and alpha I. So, how to proceed this one? Consider the standard order basis, say b equal to 1 x square of b. First, we have to obtain from this order basis the corresponding orthogonal basis. We shall find the corresponding orthogonal basis, say alpha 1, alpha 2, alpha 3, and then corresponding orthonormal basis, say b prime equal to something alpha 1 prime, alpha 2 prime, alpha 3 prime. So, first objective will be to how to find b prime. To find the orthogonal basis, we have to use the Gram-Schmidt orthogonal procedure, and then once that orthogonal vectors are obtained, divide by the magnitude of the vectors will give you orthonormal basis. So, suppose b prime is known to us, then the corresponding G will be, G will be equal to sigma phi of alpha j, and this bar, and alpha j equal to 1 to 3. Since we have taken over the real, so this phi alpha j bar is basically called to here simply phi of alpha j and alpha j, okay, j equal to 1 to 3. So, this will prime this one and prime please. Okay. So, step 1, find the corresponding orthogonal order basis. Let beta 1 equal to 1, beta 2 equal to x, and beta 3 equal to x square. So, according to Gram-Schmidt orthogonalization procedure, alpha 1, let me consider alpha 1 equal to beta 1, and then alpha 2 will be equal to beta 2 minus inner product of beta 2 and alpha 1 by norm of alpha 1 square and alpha 1. So, this implies alpha 2 equal to beta 2 equal to x minus inner product of beta 2 alpha 1 0 to 1 x and alpha 1 is 1 into dx by norm of alpha 1 that is equal to 1 and into here also 1. So, this is equal to x minus x square by 2. So, put x value 1 shall have x minus 1 by 2. So, alpha 2 equal to x minus 1 by 2. So, this implies norm of alpha 2 square will be equal to 0 to 1 x minus 1 by 2 whole square dx, that is equal to 0 to 1 x square minus x plus 1 by 4 and dx. So, this is equal to, if I integrate, I will have x cube by 3, it will be 1 by 3 minus x square by 2 1 by 2 plus x, that is equal to 1 by 4. So, if I simplify, this will be equal to 4 minus 6 plus 3 by 12. So, this is equal to 1 by 12. So, norm of alpha 2 equal to 1 by square root of this one. Then alpha 3 will be equal to beta 3 minus inner product of beta 3 and already calculated alpha 1 by norm of alpha 1 square alpha 1 minus inner product of beta 3 and alpha 2 by norm of alpha 2 square into alpha 2. So, this implies this is beta 3 equal to x square minus this will be 0 to 1 x square dx, and this will be equal to 0 to 1 x square into x minus 1 by 2 dx, and also we have alpha 2 is equal to x minus 1 by 2 and alpha 2 square equal to 1 by 12. So, this means that I am getting x square minus x cube by 3, that is 1 by 3 minus I will have 12 times x minus 1 by 2 and integral of 0 to 1 x cube minus x square by 2 dx, which is equal to x square minus 1 by 3 minus 12 x minus 1 by 2, and this will be equal to x to the power 4 by 4, that is 1 by 4 minus 1 by 6. So, this will be equal to x square minus 1 by 3 minus again 1 by 12. So, it will be x minus 1 by 2, 12 cancel. So, like this. So, alpha 3 equal to I am getting in the end your x square minus x, and this will be plus 1 by 6 if I am plus 1 by 2 minus 1 by 3. So, I have alpha 3 is equal to this one. So, we have already obtained the corresponding orthogonal order basis alpha 1, alpha 2, alpha 3. Now, also we have to calculate what is the norm of alpha 3 square. This is equal to 0 to 1, you will have x square minus x plus 1 by 6 into x square minus x plus 1 by 6 dx. So, if I calculate that one by using, I can straightway, it is very simple calculations. So, I can write down this is 0 to 1 x square minus x whole square and plus 2 into x square minus x into 1 by 6. So, it will be there, and plus 1 by 6 whole square. So, this into dx. So, if after simplifications I will have in the end your alpha 3, I can write down norm of alpha 3 whole square equal to 1 by 5 into 36. So, please consider this is the homework and check whether norm of alpha 3 whole square equal to 1 by 5 into root 36 or not. So, this implies norm of alpha 3 equal to 1 upon 6 root 5. Okay. So, we know, so then we can immediately calculate your alpha 1 prime equal to 1, alpha 2 prime equal to root over 12 into x minus 1 by 2, and alpha 3 prime equal to 6 into root over 5 into x square minus x plus 1 by 6. You can immediately cross check whether this alpha 1, alpha 2, alpha 3 are orthogonal or not. That we can check by taking the inner product of alpha 1 prime and alpha 2 prime, that must be equal to 0, or alpha 2 prime and alpha 3 prime must be equal to 0. We can quickly check it and see they are orthogonal. And once they are orthogonal, and then you also can calculate the norm of this alpha 1, alpha 2, alpha 3, and if you divide by the corresponding vectors, I will have alpha 1 prime, alpha 2 prime, alpha 3 primes. So, I have now, so let B prime, which is I am denoting as a set of all the orthonormal order basis, that is alpha 1 prime, alpha 2 prime and alpha 3 prime, which is equal to say 1 and root 12 into x minus 1 by 2 and then 6 root over 5 into x square minus x plus 1 by 6. Okay. So, then according to that last results, so your G will be the unique fixed vector in V, G will be what? So, G will be equal to summation of linear functional at alpha j prime, j equal to 1, 2, 3 and your alpha j prime. So, this is equal to See, phi of alpha j prime means alpha j prime at t naught. So, this if I simplify this one, this will be equal to alpha j prime equal to 1. So, it is 1 only plus. So, this will be, let me just write, this is basically phi of alpha 1 prime and alpha 1 prime plus phi of alpha 2 prime plus phi of alpha 3 prime and alpha 3 prime. Phi of alpha 2 equal to, we know, root over 12 into x minus 1 by 2. So, at the value of t naught, it will be root over 12 into t naught minus 1 by 2, and that function, that is alpha 2 prime, that is equal to again root over 12 into x minus 1 by 2 plus, we have in exactly same way. So, root over 5 into 6, root over 5 into 6. So, I will say 5 into 6 square, okay, into t naught square minus t naught plus 1 by 6 into x square minus x plus 1 by 6, and g is the required element in V such that your phi of f will be equal to f into g, I mean inner product of f and g, please. This is equal to 0 to 1 f of x and g of x dx. I hope this example will certainly give a clear picture about this concept. We have also seen that over a finite dimensional inner product space, if a operator T is defined, then its adjoint exists. And also we have seen that if you consider an order basis which is consisting of all orthonormal vectors, then what is the correlation between the matrix representation of T and T star with respect to orthogonal normal basis. Now, let us see for a specific operators. Let me consider, let V be an finite dimensional inner product space. Let E be the orthogonal projection of V on its subspace say W. W is a subspace of V. Then E equal to E star. I mean the corresponding adjoint operator of the E is basically E. Let us see how it is. Given E is a projection of V, and it is not only projection, it is orthogonal projections, the orthogonal projection of V, please, on W. So, this implies I can write down V equal to direct sum of W plus its orthogonal complement like this. So, this implies any element, any alpha belongs to V, alpha can be written as E alpha plus I minus E operating on alpha. We know what is the meaning of W and W orthogonal complements. Any element of W will be orthogonal to its orthogonal complement. And similarly, beta also, beta can be also written E beta plus I minus E operating on beta. we have inner product of E alpha and beta equal to alpha E star beta. We want to know what is E star for this problem. See, inner product of E alpha and beta, this is equal to, one can write down E alpha and E beta plus I minus E operating on beta. So, this is equal to inner product of E alpha and E beta. Since inner product of E alpha and I minus E operating on beta, this will be equal to 0, because this one belongs to your W complement. So, that is why this will be equal to like this. So, this is again I can read out, because the contribution of inner product of I minus E operating on beta and E beta equal to 0. So, I can rewrite this will be equal to E alpha plus I minus E operating on alpha and E beta. So, this will be equal to alpha E beta. So, this implies E star equal to E. So, if I consider a orthogonal projection operator of a vector space B on its subspace W, then the adjoint of the projection operator E will be equal to that operator itself. So, let me take examples. Consider V equal to R3 and this is standard inner product, standard inner product in V. Let E be the also orthogonal projection of V on W, where W is a subspace of V spanned by beta equal to 3, 12 minus 1. Let us see what is the matrix representation of this operator with respect to standard order basis of V. Of course, I will take standard orthonormal order basis of V, and we will also see what is the corresponding matrix representation of E star. According to theorems, we have seen that E equal to E star. Now, let us check whether this is correct through in this example or not. Okay. So, let alpha equal to x comma y comma z be any element of V. Define E alpha equal to, since orthogonal projection of alpha means I am talking about the best approximations of alpha in W. So, then E alpha will be equal to what? E alpha will be your inner product of alpha and beta divided by norm of beta square and beta. This is already we have seen in last 2-3 classes. I think if you recall, the best approximation of a vector in an inner product space. So, accordingly I can write down that E alpha will be like this. So, this will be equal to your alpha equal to x y z. I have taken the inner product, it's standard inner product. So, therefore, I will have 3x plus 12y minus z by your norm of beta will be 3, okay, this will be equal to your 9 plus 12 square plus 1, and then this will be 3 12 minus 1. So, if I simplify, I am getting here 154 into 3x plus 12y minus z into the vector 3 12 minus 1. So, E alpha equal to like this. So, consider the orthonormal basis E1 is equal to 1 0 0, E2 equal to 0 1 0, E3 equal to 0 0 1 of V. So, let me consider this standard orthonormal order basis like this. So, then E of E1 will be equal to, I am getting this will be equal to 154, that will be there, x will be replaced by 1 and y and z is 0. So, this will be equal to 9 36 and minus 3. So, if I consider the matrix representation of E with respect to the order basis B star, if I denote this is equal to say B, let me consider this one. Okay. So, this order basis is italic B, then yeah, this will be equal to the first column will be then 1 by 154 will be there, because this factor will be common to all. So, therefore, I have written taken out 1 by 154, and then 9 36 minus 3, and E2 will be equal to again 154. So, 36, yes, 144 and 36 144 and minus 12, 36 144 and minus 12, yeah. So, I will have 36 144 and minus 12, and E of E3 will be equal to again 154 and z equal to 1. So, minus 3 minus 12 and plus 1, minus 3 minus 12 and plus 1. So, I see this is the matrix which is symmetric. So, definitely and over the real. So, it will be equal to the transpose. I mean, so this implies the matrix representation of E with respect to B, this one equal to suppose A, and so A equal to A transpose. So, this equal to basically matrix representation of E star with respect to same order basis. So, we see that here the matrix representation of the projection operator E is basically symmetric matrix. So, since it is defined over the real line, and therefore, matrix representation of E and E transpose both are same, but here if I do not take orthonormal basis, then it is not easy to correlate the matrix representation of E and its corresponding E star. Since we do not have much time here, so I could not write down it here, but certainly you will get it in the assignment sheet.